Hello viewers, I Nilofer welcome you to the chapter of dispersion or variations. In this unit we'll study the meaning of variation and methods of studying variation. Before proceeding to study the various kinds of variations such as the range, the interquartile range, quartile deviation, average or mean deviation, standard deviation and the variance, we'll first acquaint ourselves with the terms which are going to be used in the discussion. In the preceding chapter, we presented some methods for measuring the central tendency of the quantitative data set. Distribution is the spread of the data in a distribution, that is, the extent to which the observations are scattered. The degree of scatter of an individual observation is measured by measuring the distance between the average and the individual observation of the given data set. It is the simplest method of measuring dispersion. Range is defined as the difference between the value of the smallest item and the value of the largest item included in the distribution. In other words, the range of a data set is equal to the largest measurement minus the smallest measurements. Symbolically, range is equal to capital L minus capital S, where capital L is the largest value and capital S is the smallest value. The relative measure corresponding to range, called the coefficient of range, is obtained by applying the following formula. Coefficient of range is equal to capital L minus capital S divided by capital L plus capital S. Let's see an example here. The following are the prices of shares of XYZ Company Limited, so from Monday to Saturday. Now we are supposed to calculate range and its coefficient. Let's see the solution. We have the formula for range is equal to L minus S. Hence we know that L here is 450 and S is 150. So range will be 450 minus 150, which gives you rupees 300. Also calculate the coefficient of range, which is calculated as L minus S divided by L plus S. So that is equal to 450 minus 150 divided by 450 plus 150, which gives you 300 upon 600, that is equal to 0.5. Some of the merits are: amongst all the methods of studying dispersion, range is the simplest to understand and the easiest to compute. Second point, it takes a minimum time to calculate the value of range. Third merit, hence if one is interested in getting a quick rather than a very accurate picture of the variability, one may compute range. Let's look at the demerit. First one, range is not based on each and every item of the distribution. Second, it's subject to the fluctuations of considerable magnitude from sample to sample. Third one, range cannot tell us anything about the character of the distribution within the two extreme observations. For example, observe the following series in the given table below. In all three series, range is same, that is 40, which is calculated as 46 minus 6, but it does not mean that the distributions are alike. The range takes no account of the form of the distribution within the range. Therefore, range is most unreliable as a guide to the dispersion of the values within a distribution. Now let's see the fourth demerit of it. Range cannot be computed in case of open-end distributions. The interquartile range is a measure of variability based on dividing a data set into quartiles. In other words, It represents the difference between the third quartile and the first quartile. Symbolically, interquartile range is given as Q3 minus Q1. Very often, the interquartile range is reduced to the form of the semi-interquartile range or quartile deviation by dividing by 2. Symbolically, quartile deviation, we get it as Q3 minus Q1, the whole thing divided by 2. The quartile deviation gives the average amount by which the two quartiles differ from the median. In a symmetrical distribution, the two quartiles Q1 minus Q3 are the equidistant from the median. That is, median minus Q1 is equal to Q3 minus median, and as such, the difference can be taken as a measure of dispersion. Quartile deviation is an absolute measure of dispersion. The relative measure corresponding to this measure is called the coefficient of quartile deviation and is calculated as follows. Coefficient of quartile deviation is equal to Q3 minus Q1 divided by Q3 plus Q1. Coefficient of quartile deviation can be used to compare the degree of variation in different distributions. The process of computing quartile deviation is very simple since we have just to compute the values of the upper and the lower quartiles. The following illustration would clarify the calculations. Let's see this illustration. Calculate coefficient of quartile deviation from the following data. Now we have a table here representing the marks and the number of students. Now let's see the solution. We are doing the calculation of coefficient of quartile deviation. For this, we are making a table with columns added as marks, number of students, and cumulative frequency, that is CF, as given in the table. So we have Q1 is equal to size of n plus 1 by 4th item. So that is equal to size of 43 plus 1 by 4, that is equal to 11th item. Now the size of the 11th item is 20, hence Q1 is 20. Now let's see how do we calculate Q3. Q3 is equal to size of 3 times n plus 1 divided by 4th item. So that is equal to size of 3 into 43 plus 1 divided by 4. So that is equal to 33rd item. Now the size of the 33rd item is 40. Hence Q3 is 40. So we have Q1 and Q3 with us. Now we'll calculate QD, that is quartile deviation, which is equal to Q3 minus Q1 divided by 2. So that is equal to 40 minus 20 divided by 2, which gives us 10. Now we'll calculate the coefficient of quartile deviation. The formula is Q3 minus Q1 divided by Q3 plus Q1. So that is equal to 40 minus 20 divided by 40 plus 20, which is equal to 0.333. Merits are: first one, quartile deviation is simple to comprehend and easy to compute. Second one, it is quite satisfactory if one is concerned with main body, the middle half of the series, and cares nothing about the extreme variation. Third point, it is useful in studying dispersion in open-end series. Demerits are: the first one, quartile deviation has a serious drawback in that it is not based on all the values of the variable, and so it does not take into account the variation of each observation about the average. Second one, it is not capable of further algebraic treatment. It merely indicates a distance of scale. Third demerit, it is affected considerably by fluctuations in sampling. The two methods of dispersion discussed above, namely range and quartile deviations, are not measures of dispersion in the strict sense of the term because they do not show the scatter around an average. However, to study the formation of a distribution, we should take the deviations from an average. The two other measures, namely the average deviation and the standard deviation, helps us in achieving this goal. The average deviation is sometimes called as the mean deviation. It is the averages differences between the items in a distribution and the median or mean of that series. Theoretically, there is an advantage in taking the deviations from the median because the sum of the deviations of items from median is minimum when signs are ignored. In other words, it is the sum of the deviations from an average divided by the number of items in a distribution. The formula for computing mean deviation is mean deviation, or we can write it as MD, is equal to sigma absolute D divided by N, where absolute D within the parallel lines denotes deviation from median ignoring the signs. Now let's see an example. Calculate the mean deviation of the two wages groups of 5 and 7 members given below. So let's see the solution to this. Calculation of the mean deviation is done as follows. Mean deviation for the first group, we are calculating MD is equal to sigma of absolute D divided by capital N. The absolute D is equal to deviation from the medians ignoring the signs. So median is equal to N plus 1 divided by 2th item. So that is equal to size of 5 plus 1 divided by 2, which is equal to third item. So the size of the third item is 4,400. So sigma absolute D is equal to 1,200 from the table, and capital N is 5. Now MD is equal to 1200 divided by 5, which gives you 240. So this means that the average deviation of the individual wages from the median wages is rupees 240. Now let's calculate the mean deviation in case of the second group. Median is equal to N plus 1 by 2th item. So that is equal to size of 7 plus 1 by 2, that is equal to 4th item. Size of the 4th item is 4,400. Now again from the table we have sigma of absolute D is equal to 4,400 and N is equal to 7. So mean deviation is calculated as 4,400 divided by 7, that is equal to 571.43. If we compute the coefficient of median deviation, we shall divide mean deviation by median. Thus for the first group, coefficient of mean deviation is equal to 240 divided by 4,400, that is equal to 0.055. And for the second group, coefficient of mean deviation is equal to 571.43 divided by 440, which gives you 0.13. The formula for computing mean deviation is mean deviation is equal to MD, that is equal to sigma F into absolute D divided by N, where absolute D denotes a deviation from the median ignoring the signs. Now let's see an example. The numbers of telephone calls received at an exchange in 245 successive 1-minute intervals are shown in the following frequency distribution. We have to compute the mean deviation about the median. So table of the number of calls and frequency is given here. Let's see the solution. In the solution, we are doing the calculation of mean deviation from median. For that, we are making a table with column headed as number of calls, frequency, cumulative frequency, absolute D, and F times absolute D. So calculate sigma F times absolute D divided by N from the table first. Now we have MD is equal to sigma F times absolute D divided by N. So median is the size of N plus 1 by 2th item, that is the size of 245 plus 1 by 2, that is equal to 1/23rd item. Hence median value is 4. Now the mean deviation is calculated as 366 divided by 245, which is giving us 1.494. The procedure remains the same as discussed above for calculating mean deviation in continuous series. The only difference is that here we have to obtain the midpoints of the various classes and take the deviations of these midpoints from the median. The formula for computing mean deviation is same, that is mean deviation or MD is equal to sigma F times absolute D divided by capital N, where absolute D denotes a deviation from median ignoring the signs. Now let's do an example. Calculate the mean deviation from the following table. From the following table, we have the column marks and number of students. So we have a solution to this, that is, we have to do the calculation of mean deviation from median. For that, we are making a table with the columns marks, small m, which is nothing but the mid value, then f frequency, then cumulative frequency, then we have absolute d column, and then the last column is f times absolute d. So we can calculate here n is equal to 60 and sigma f times absolute d is equal to 68 from the table. We see that median is again the size of n divided by 2th item. So that is the size of 60 by 2th item, that is equal to 30th item. Median lies in the class 40 to 50. Now we have a formula to calculate median in this case. Median is equal to capital L plus n by 2 minus Cf, the whole thing, divided by f times I. So we have L equal to 40, n by 2 is the 30th item, Cf is equal to 20 and I is equal to 10. Plugging all these values in the formula, we get MD is equal to 40 plus 30 minus 20 divided by 20 into 10. So that is giving us 40 plus 5, which is giving us 45. Now median is equal to sigma f times absolute d divided by n into I. Now sigma f times absolute d is equal to 68, n is equal to 60, I is equal to 10. Now we have MD is equal to 68 by 60 into 10. That gives us 11.33. This concept was introduced by Carl Pearson in 1893. It is by far the most important and widely used measure of studying dispersion. Its significance lies in the fact that it is free from those defects from which the earlier method suffers and satisfies most of the properties of a good measure of dispersion. It is also known as root mean square deviation for the reason that it is the square root of the means of the squared deviations from the arithmetic mean. Standard deviation is denoted by the small Greek letter sigma. The standard deviation measures the absolute dispersion or variability of distribution. The greater the amount of dispersion or variability, the greater the standard deviation, the greater will be the magnitude of the deviation of the values from their mean. A small standard deviation means a high degree of uniformity of the observation as well as homogeneity of a series. A large standard deviation means just the opposite. Thus, if we have two or more comparable series with identical or nearly identical means, it is the distribution with the smallest standard deviation that has the most representative mean. Hence, it is extremely useful in judging the representativeness of the mean. Both are based on each and every item of the distribution, but they differ in the following respects. First one, algebraic signs are ignored while calculating mean deviation, whereas in the calculation of standard deviation, signs are taken into account. Second, mean deviation can be computed either from median or mean, but the standard deviation, on the other hand, is always computed from the arithmetic mean, because the sum of the squares of the deviations of items from arithmetic mean is the last. In this method, standard deviation can be computed by applying any one of the following two methods. By taking deviations of the items from the actual mean, symbolically sigma is equal to under root sigma x squared divided by n, where x is equal to x minus x bar and n is equal to number of observations. Now let's see an example. Calculate standard deviation from the following observations of marks of 5 students of a tutorial group. Mark out of 25, we have these marks 8, 12, 13, 15, 21. Now let's see the solution to this. We are doing the calculation of standard deviation. For that, we are making a table with columns capital X, second one x minus x bar, which is equal to small x, and the third one x squared. From the table, we can calculate sigma x is equal to 70, sigma small x is equal to 0, and sigma x square is equal to 106. So we are taking the formula sigma is equal to under root sigma x square divided by n, where x is equal to x minus x bar. So x bar is equal to sigma x divided by n, so that is equal to 70 by 5, which gives you 14. So sigma x square is equal to 106 and capital N is equal to 5. Now plugging all these values in the formula, we get sigma is equal to under root sigma x square divided by n, which is equal to under root of 106 divided by 5. So that is equal to under root of 21.2, which is equal to 4.604. The second part, by taking the deviation of the items from an assumed mean, symbolically sigma is equal to under root sigma d square divided by n minus sigma d divided by n those whole square, where we can see this d is equal to capital X minus a, where a is the assumed mean and capital N is the number of observations. So let's see an example here. The following figures give the daily wage of 10 laborers in rupees. Find the standard deviation. So we have these numbers 227, 235, 255, 269, 292, 299, 312, 321, 333 and 348. So we are doing the calculation of standard deviation in the solution. We are making a table with capital X, x minus 200 because 200 is taken as the assumed mean, and d square. Now from the table we calculate n is equal to 10. So sigma d is equal to 91, that we can calculate, and sigma d square is equal to 16,223. Now apply the formula. Sigma is equal to under root sigma d square divided by n minus sigma d by n those whole square. So we are plugging in all the values here. Again we can see that d is equal to capital X minus a. So sigma d square is calculated as 16,223. Now capital N is 10 and sigma d is equal to 91. Putting all these values in the formula, we get sigma is equal to under root of 16,223 divided by 10 minus 91 divided by 10 those whole square. So under root 1622.3 minus 82.81. So that is giving us 39.24. In this method, for calculating standard deviation, any of the following methods may be applied. So we have these methods. The first one is actual mean method. In this, symbolically we can represent the formula as sigma is equal to under root sigma fx square divided by capital N, where small x is the x minus x bar. In the case of assumed mean method, that is the other method, the formula can be symbolically represented as sigma equals to under root of sigma ft square divided by capital N minus sigma ft divided by n the whole square, where again we have small d is equal to capital X minus a, where a is the assumed mean and n is the number of observations. So let's see an example. Calculate the standard deviation from the data given below. So we have a table of size of items and frequency. Now in the solution we are doing the calculation of standard deviation. For that we are making a table with columns added as size of items, second one frequency, third one x minus 6.5, that is small d, then we have ft column, and then we have the last column which is ft square. Now from the table we are applying the formula sigma is equal to under root of sigma ft square divided by n minus sigma ft by n those whole square, where small d is capital X minus a. Now from the table we have calculated sigma ft square is as 362, sigma ft as 128, and capital N is equal to 217. Now putting these values in the formula, we get sigma is equal to under root of 362 divided by 217 minus 128 divided by 217 those whole square. So that is equal to under root of 1.67 minus 0.59 square. So that is equal to under root of 1.67 minus 0.35, which is giving us 1.149. Now let's see the third method, that is the step deviation method. This method is symbolically represented as sigma equals to under root of sigma ft square divided by capital N minus sigma ft divided by n the whole square, into I, small I, where d, small d is x minus a divided by small I, and I is nothing but here class interval. Alright, now let's see an example. Find the standard deviation for the following distribution. So we have a table of x and f. We are doing the calculation of standard deviation again in the solution. So we are making a table of x, f, and x minus 34.5. 34.5 is what we have taken as assumed mean. So the third column is x minus 34.5 divided by 10. That is equal to small d. Then we have ft column. Then the last one we have ft square. So we are applying the formula sigma is equal to under root of sigma ft square divided by capital N minus sigma ft by n, those whole square, into I. So again, where d is equal to x minus a by I. Now from the table we have calculated sigma ft square as 130, sigma ft as 22, capital N as 70, and I is 10. Putting all these values in the formula, we get sigma is equal to under root of 130 by 70 minus 22 by 70, those whole square, into 10. So that is equal to under root of 1.857 minus 0.1 into 10, that is equal to 1.326 into 10, that gives us 13.26. In continuous series, any of the methods discussed above for the discrete distribution can again be used. However, the mostly step deviation method is used. Symbolically here, the formula can be represented as sigma equals to under root of sigma ft square divided by capital N minus sigma ft divided by capital N, those whole square, times I, where d is here small m minus a divided by I. So small m is nothing but the midpoint, I is the class interval, and a is the assumed mean. Now let's see an example for this. Find the standard deviation for the following distribution of income of 100 families in a village. So we have a table of income in rupees and number of families. So in the solution we are calculating the standard deviation. For that we are making a table with income in rupees. The next second column midpoint, that is small m. Third one frequency, that is small f. Next one m minus 2500 divided by 1000, that is small d. ft column, and the last one we have ft square column. The formula that we are using here is sigma is equal to under root of sigma ft square divided by n minus sigma ft by n, those whole square, times I. So from the table we have sigma ft square is equal to 186, sigma ft is equal to minus 18 that we have calculated from the table, capital N is 100, and I here is 1000. Now putting these values in the formula, we get sigma is equal to under root of 186 divided by 100 minus, in the bracket, minus 18 by 100, those whole square, times 1000 is equal to under root of 1.86 minus 0.0324 times 1000, that is equal to 1.3519 times 1000, which is equal to 1351.9. The term variance was used to describe the square of standard deviation by R.A. Fisher in 1918. Variance is highly important in advanced work where it is possible to split the total into several parts, each attributable to one of the factors causing variation in the original series. Variance is defined as follows. Variance is equal to sigma x minus x bar square divided by n. This variance is nothing but the square of the standard deviation. That is, variance is equal to sigma square, or sigma is equal to under root of variance. So sigma is equal to under root of variance, where variance is nothing but that is equal to sigma ft square divided by n minus sigma ft by capital N, those whole square, times I. Again, small d here is equal to small m minus capital A divided by I. So I is a class interval, small m is a midpoint here. Now for this we are taking an example again. The weights of a number of packages are given as follows. We have these weights with us: 16.1, 15.9, 15.8, 16.3, 16.2, 16.0, 15.9, 16.0, 16.1, 16.0, 15.9, 16.1, 16.0 and 16.0. Now from the frequency table, find the standard deviation and the variance. So let's see the solution. Let's make a table with the columns headed as weights, that is capital X, then frequency, that is small f, third one x minus a, that is equal to small d, next one ft column, and the last one ft square column. We are using the formula sigma is equal to under root of sigma ft square divided by n minus sigma ft by n those whole square. Now from the table we have sigma ft square is equal to 0.31. We can calculate that. Sigma ft is equal to minus 1.1 and n is equal to 14. Now putting these values in the formula, we are getting sigma equals to under root of 0.31 divided by 14 minus, in the bracket, minus 1.1 divided by 14 those whole square. So we are getting under root of 0.022 minus 0.0062, which is equal to 0.126. Now let's calculate the variance as well. This is sigma that we have calculated. So variance is nothing but the sigma square is equal to 0.126 square. So that is equal to 0.0159. So finally we have learned today the introduction of measures of variation. We have discussed about methods of variations or dispersion and determined the three methods of mean deviation and standard deviation. Apart from this, the types of variation such as range, quartile, mean and standard deviation are also discussed, along with the merits and demerits as well. So that finally brings us to the end of today's episode. We are ending here the chapter of measures of dispersion, and we'll see you again discussing about our next topics on more wide variety. Till then, have a nice time and thank you. Bye.